Chapter 9 starts talking about statics and torque. These are different types of forces. So, a lot of chapter 4 is going to be incorporated into this chapter. And you'll see exactly how we can manipulate some of the equations we already know from chapter 3 and 4 into torque. So, statics is the study of forces in equilibrium, a large group of situations that makes up a special case of Newton's second law. We have already considered a few such situations. In this chapter, we cover the topic more thoroughly, including consideration of much possible or such possible effects as the rotation and deformation of an object by the forces acting on it. So, the first condition of equilibrium, you obviously have your figure right here with the free body diagram on the right side. You have your weight pointing downwards towards the center of the earth and your normal force pointing upwards. The first condition necessary to achieve equilibrium is the one already mentioned. The net external force on the system must be zero. Expressed as an equation, this is simply F net equals zero. Note that if F net equals zero, then the net external force in any direction is zero. For example, the net external forces along the x-axis and y-axis are zero, so we can respectively write them as net F net x equals zero and F net y equals zero. So this motionless person is in static equilibrium. The force acting on it and acting on him add up to zero. Both forces are vertical in this case, obviously because there's no x force in the either positive or x direction. This car is in dynamic equilibrium because it is moving at a constant velocity. Since the velocity is zero, acceleration is zero, therefore my force is zero. There are horizontal and vertical forces, but the net external force in any direction is zero. The force applied, FAP, P, between the tires and the road is balanced by air friction, and the weight of the car is supported by the normal forces, here shown to be equal for all four tires. So you see how from our free body diagram, we have the normal forces and the weight cancel out, and the force of friction and the force applied cancel out as well. So the net external force of the overall system is zero. However, it is not sufficient for the net external force of a system to be zero for the system to be in equilibrium. Consider two situations involving a hockey stick. Forces are applied to the ice hockey stick lying flat on ice. The net external force is zero in both situations, but in one case, equilibrium is achieved, whereas in the other, it is not. The next slide, the ice hockey stick remains motionless, but in figure 9.5, which the same force is applied in different places, the stick experiences acceleration rotation. Therefore, we know that the point at which a force is applied is another factor in determining whether or not the equilibrium is achieved. So you see here an ice hockey stick lying flat on ice. You have forces on both directions here. So here, the net external force is zero. Equilibrium is achieved, which is static equilibrium in this case. But when the same forces are applied on different points, the hockey stick will experience a force on top and on the bottom, causing it to rotate. Here, the net force is technically zero, but does not achieve equilibrium per se. So even though x forces on here from the left and the right side are zero, they equal zero, the points on where the forces are applied are the reason why this is in equilibrium. Okay, so that brings us to the second condition. The second condition necessary to achieve equilibrium involves avoiding accelerated rotation, maintaining a constant angular velocity. A rotating body or system can be in equilibrium if its rate of rotation is constant and remains unchanged by the forces acting on it. To understand what factors affect rotation, let us think about what happens when you open an ordinary door by rotating on its hinges. Several familiar factors determine how effective you are in opening the door. First of all, the larger the force, the more effective it is on opening the door, obviously. The harder you push, the more rapidly the door opens. Also, the point at which you push is crucial. If you apply the force too close to the hinges, the door will open slowly, if at all. Most people have been embarrassed by making this mistake and bumping up against the door when it did not open quickly as expected. Finally, the direction in which you push is also important. The most effective direction is perpendicular to the door. We push in the direction almost instinctively. So basically, if you're trying to open the door right where the doorknob is, it'll open pretty easily and smoothly. But if you're trying to open the door by the hinges or towards the center of the actual door, it'll be a little bit more difficult. You might still open it, but you'd have to have a greater force applied. So here you have 6 different ways to open the door, or for this lever arm. For A, well, first of all, torque is the turning or twisting effectiveness of the force, illustrated here for door rotation on its hinges. Torque has both magnitude and direction, so torque is a vector. So for A, we have a force here applied at the very edge. We have a radius, and the force is pointing this direction. So counterclockwise torque is produced by this force, which means that the door will rotate in a counterclockwise way due to the force. Note that the radius perpendicular is a perpendicular distance of the pivot from the line of action of the force. This is called the perpendicular lever arm. That's what this radius arm is. For B, we have the same, a smaller counterclockwise torque is produced by a smaller force, F prime in this case, acting at the same distance from the hinges, which is from the pivot point, right here. Just the differences between these two are that the force is smaller. For C, we have the same force as A, but now we're at half the distance. For D, the same force as A, but now we're pointing it in the opposite direction at the same radius. For E, a smaller counterclockwise torque is produced by the same magnitude force acting at the same point, but in a different direction, here at less than 90 degrees. And this means that these forces over here for A, B, C, D, we're at 90 degrees depending on how far or where we're at, actually applying that force on the door, on the lever arm. Here we're applying it at an angle. You see? It's not exactly 90 degrees. It's not perpendicular to the lever. So since we're adding the same force but at an angle, this lever arm is going to open slower. And for F, the torque is 0 here since the force just pulls on the hinges, producing no rotation. So the force is just pulling on it. They're at the edge of the door. So these 4 will open the door effectively. This one might be closing it depending on where the door opens and closes. This one's going to open it slowly, and this one's also the exact same force, but there's no torque being produced because it's actually on the door. It's perpendicular. The force is perpendicular to the door. So for torque, the magnitude, direction, and the point of application of the force are incorporated into the definition of the physical quantity called torque. Torque is a rotational equivalent of force. So force and torque are pretty much the same thing. Just depends if one is circular or angular, and if the other one is linear. It is a measure of effectiveness of a force in changing or accelerating a rotation, changing the angular velocity over a period of time. In equation form, the magnitude of torque is defined by torque, which is that squiggly T, equals R, your force that's applied, and sine theta at whatever angle your force is actually being applied. So if we go back to this one for E, we would have a angle as well, but at a different at a smaller pace. So if it's sine of 90, like all these A, B, C, D are, those would be sine 90 is 1. So you just have your R times your force. Since you have a sine of another angle now, it'll change the whole equation. So an alternative expression for torque is given in terms of perpendicular lever arm, which is your R perpendicular equals R sine theta. So if we have your radius and your force, if we have that R perpendicular, which means that your force is being applied at 90, that sine of 90 is going to be 1. Therefore, we just have R perpendicular and the force. So going back to the original hockey stick example, we have for A, the three factors are F, R, F, and theta, which we were just told. And these are shown here, with the point being on the end of the hockey stick down here. So R is the distance from the chosen pivot point to the point where the force is applied. So just the straight radius. You don't have to follow the line of the actual hockey stick. It's the radius right across. Where F is applied, and theta is the angle between F and the vector directed from the point of application to the pivot point. So whatever angle this actual line causes. If the object can rotate from point A, it will rotate counterclockwise. This means that the torque is counterclockwise relative to pivot A. So obviously if the force is being applied here, it's going to rotate in this manner here, with the pivot point with the center of it being here in A. For B, we have it at the top of the hockey stick. We have the nail at the top, so that's a different pivot point, which is point B. The torque from the applied force will cause a clockwise rotation around B. So it'll rotate clockwise, meaning that the torque is clockwise relative to B. So pivot point, like we mentioned, is very important when it comes to torque. The SI unit for torque is Newton times meters, usually written as Nm. For example, if you push perpendicular to the door with the force of 40 newtons at a distance of 0.8 meters from the hinges, you exert a torque of 32 newtons per meter. And when you plug it all in, it'll be 0.8 for the R times your force, which is 40 N, times sine of 90. So that just goes to 1. And it's relative to the hinges. If you reduce the force to 20, the torque is reduced to 16, and so on and so forth. So the force is very important when it comes to torque. The torque is always calculated with reference to some chosen pivot point. For the same applied force, a different choice for the location of the pivot will give you a different value for your torque, since R and theta depend on the location of the pivot. Note that the rotation in the flat plane, torque has two possible directions. Torque is either clockwise or counterclockwise relative to the chosen pivot point, as seen with the hockey stick before. Also, the magnitude of the torque is greater when the lever arm is longer. So obviously if this radius for torque is larger, that'll mean your torque is larger. Now, the second condition necessary to achieve equilibrium is that the net external torque on the system must be 0. An external torque is one that is created by an external force. You can choose the pivot around which the torque is calculated, the pivot point. The point can be a physical pivot point on the system or any other point in space, but it must be the same point for all torques. The second condition necessary to achieve equilibrium is stated by the equation your net torque is equal to 0. Torques which are in the opposite directions are assigned opposite signs. A common convention is to call counterclockwise CCW torques positive and clockwise CW torques negative. So that brings us to example 9.1. The two children shown are balanced on the seesaw of negligible mass. So we're not taking the mass of the seesaw. This assumption is made to keep the example simple. More involved examples will follow. The first child has a mass of 26 kilograms and sits 1.6 meters from the pivot A. So the pivot point would be here in the center. If the second child has a mass of 32 kilograms, how far is she from the pivot? And for B, what is FP, the supporting force exerted by the pivot? So we know that torque is RF sine of theta, but we know that theta here is 90 degrees because they are sitting perpendicular to this actual balance. So we take that as 1. So sine of theta is equal to 1 for all forces here. So that means we have our R perpendicular here. So our first equation is tau. That's what the official name of this T is, tau is equal to R1 times W1, which is just the weight of the first child. And for the second one is tau 2 equals negative R2 weight 2. Because remember, we said that clockwise was negative and counterclockwise was positive. So the third would be the pivot point, FP. But we know that they're not moving, they are balanced. So we know that FP, or the tau P, is equal to 0. For here, for equation purposes, our RP here is the center. That's the balance point. That's the pivot point. So since we're taking that to be the pivot point, we know that the radius here is 0. We're still going to try to find what FP is, but we know that the radius is 0, so tau P is 0. So again, note that the minus sign has been inserted into the second equation because the torque is clockwise and is therefore negative by convention. Since FP acts directly on the pivot point, the distance RP is 0. A force acting on the pivot cannot cause a rotation, just as pushing directly on the hinges on the door will not cause it to rotate. So now we're going to dive into the second condition of for equilibrium, is that the sum of all torques on both children is 0. So if they're both 0, that means that they equal each other, right? Because if you do tau 1 plus tau 2, that should give you 0, which means that we can equal them to each other. Which also means we can equal them to both of the first two equations. Tau 2 was negative R2 W2, and tau 1 was R1 W1. But by inserting this negative here, we can get rid of the negative from here. They cancel each other out. And now substituting the M and G, mass 2G, and mass 1G for our W2 and W1, when we can rearrange that to find our R2, the radius of the second child. Because we know R1 is 1.6 meters, our mass 1 is 26 kilograms, and mass 2 is 32. So plugging that all into a calculator, we get 1.3 meters. That's how far the second child is sitting. So that brings us to, for B, we are going to find this FP. Well, we know that all forces are 0 because it is at equilibrium. So we know that Fy is 0, right? Fx is also 0, but we don't need it in this problem here. So all forces acting on that pivot point is the force of the pivot point. We also have to take into account both of the masses of the weights of the two children that are pointing downwards. We have W1 and W2 pointing downwards, and we have FP pointing upwards. So if we're finding for FP, can move both of these, adding them together to the right side. And we know M1G and M2G. Plugging that into the equation here, and we get 568 newtons. So if we knew that from the beginning, we could plug that into this equation, but it would still give us a 0 because you're multiplying by 0. But that's what the force on that pivot point is exerting upwards, to keep both the children balanced on the seesaw. Okay, so that brings us to stability. It is one thing to have a system in equilibrium. It is quite another for it to be stable. There are 3 types of equilibrium: stable, unstable, and neutral. A system is said to be stable if, when displaced from equilibrium, it experiences a net force or torque in a direction opposite to the direction of the displacement. For example, a marble at the top of a bowl will experience a restoring force when displaced from its equilibrium position. This force moves it back towards the equilibrium position. Most systems are in equilibrium position, especially for small displacements. A system is in unstable equilibrium if, when displaced, it experiences a net force or torque in the same direction as the displacement from equilibrium. A system is unstable equilibrium accelerates away from its equilibrium position if displaced even slightly. An obvious example is a marble resting on the top of a hill. Once displaced, it accelerates away from the crest of the hill, away from its original point. A system is in neutral equilibrium if its equilibrium is independent of displacements from its original position. A marble on a flat horizontal surface is an example, because the marble is not going to go anywhere. It's just going to sit there until there's a net external force acting on it. Combination of these three situations are possible though. For example, a marble on a saddle is stable for displacements towards the front or back of the saddle and unstable for displacements on the side. So here, what kind of equilibrium is this? A man balances a toy doll on one hand. So for here, we have our center of gravities. It seems to be very centered, but if the toy doll was even slightly moved towards the left or the right, it would become unstable. So here, the pencil is in the condition of equilibrium. The net external force on the pencil is 0, and the total force or total torque about any pivot is also 0. So that pencil is not going to move unless there's an external force. So it's in stable equilibrium here. Here we have also a stable equilibrium. If the pencil is displaced slightly to the side, which is in this case counterclockwise, it is no longer in equilibrium. Its weight produces a clockwise torque that returns the pencil towards equilibrium position. So even though it's slightly displaced, we know that if you let go of this pencil, it will come back down and become stable again. Here, though, the pencil is displaced even greater. If this pencil were to be released at this angle, the pencil would go away from its original pivot point, its original setting. So this is unstable equilibrium. Here, even though you can have it balanced perfectly on the tip of the pencil, technically at this moment, this is stable equilibrium. Now, once it is slightly displaced like it is here, then it becomes unstable because we know that automatically that pencil is going to come over. All right, for these two, for A, the center of gravity which is CG here, of the sphere on a flat surface lies directly above the point of support, independent of the position of the surface. The sphere is therefore in equilibrium in any location and is displaced, it will remain put. So the marble here, the sphere, is in perfect equilibrium here, which is also called neutral equilibrium. Because at any point, even though it's rolling, it may stop and it'll still be at equilibrium. For B, because it is a circular cross section, the pencil is in equilibrium for displacements perpendicular to its length. But what kind of equilibrium? Here it's again neutral because we can just imagine that we're looking at the pencil from the very back. It'll still look like a sphere. So therefore, since the sphere is at equilibrium, the pencil is also at equilibrium. When we consider how far a system is stable, in stable equilibrium can be displaced before it becomes unstable, we find that some systems in stable equilibrium are more stable than others. The critical point is researched when the center of gravity, CG, is no longer above the base of support. Consider a person since the CG of a person's body is above the pivots in the hips. Displacements must be quickly controlled. This control is a central nervous system function that is developed when we learn to hold our bodies erect as infants. For increased stability, while standing, the feet should be spread apart, giving a larger base of support. Stability is also increased by lowering one's center of gravity by bending the knees, as when a football player prepares to receive a ball or braces themselves for a tackle. A cane, a crutch, or a walker increases the stability of the user even more as the base of the support widens. Usually, the center of gravity of a female is lower, closer to the ground, than a male. Young children have their center of gravity between their shoulders, which increases the challenge of learning how to walk. So here for A, you have our free body diagram. This person is standing straight up. So for the center of gravity of an adult, is above the hip joints, one of the main pivot points of the body, and lies between two narrowly separate feet. Like a pencil standing on its eraser, this person is in stable equilibrium in relation to sideways displacements. But relative small displacements take his center of gravity outside of the base of support and makes him unstable. Humans are less stable relative to forward and backward displacements because the feet are not very long. Muscles are used extensively to balance the body in the front to back direction. For B, while bending in the manner shown, stability is increased by lowering the center of gravity. Stability is also increased if the base is expanded by placing the feet farther apart. So here for this chicken, the center of gravity of a chicken is below the hip joints. The chicken is in stable equilibrium. The body of the chicken is supported from above the hips and acts as the pendulum between them. Even relatively large displacements of the chicken's center of gravity are stable and result in restoring forces and torques that return the center of gravity to its equilibrium position with little effort on the chicken's part. So engineers and architects strive to achieve extremely stable equilibriums for buildings and other systems that must withstand wind, earthquakes, and other forces of displace them from equilibrium. Although the examples in this section emphasize gravitational forces, the basic conditions of equilibrium are the same for all types of forces. The net external force must be zero, and the net torque must also be zero. So some problem-solving strategies for this. The first step is to determine whether or not the system is in static equilibrium. This condition is always the case when the acceleration of the system is zero and accelerated rotation does not occur. So force is zero, torque is zero. It is peculiarly important to draw a free body diagram for the system of interest. Carefully label all forces and note their relative magnitudes, directions, and points of application whenever these are shown. Remember, the point of application is important here for torque. The third thing you should do is solve the problem by applying either or both of the conditions for equilibrium. So that means the net force equals zero and or the net torque equals zero, depending on the list of known and unknown factors. If the second condition is involved, choose the pivot point to simplify the solution. Any pivot point can be chosen, but the most useful ones cause torques by unknown forces to be zero. The torque is zero if the force is applied at the pivot or along a line through the pivot point. Always choose a convenient coordinate system for projecting forces. So just like the example that we did, 9.1, where we chose the pivot point to be on the actual balance. So that means our torque on the pivot point was zero because our radius was zero. That was a convenient thing that we did. And 4, check the solution to see if it is reasonable by examining the magnitude, direction, and the units of the answer. The importance of this last step never diminishes, although in unfamiliar applications, it is usually more difficult to judge reasonableness. These judgments become progressively easier with experience. This is something that we've been doing since chapter 1 and chapter 2, where you have to make sure that, okay, well, my direction is right, my magnitude makes sense. You have to take into account how the problem was set up and what your answer is. If your answer doesn't make sense, like before we would say, okay, there is no negative time. Well, if you get a negative time, it doesn't make sense. You have to make sure that your answer is reasonable for your problem. So for figure 9.19, a pole vaulter holds a pole horizontally with both hands. Now let us apply this problem-solving strategy to the pole vaulter here. The pole is uniform and has a mass of 5 kilograms. The pole's center of gravity lies halfway between the vaulter's hands. It seems reasonable that the force exerted by each hand is equal to half the weight of the pole, or in this case, 24.5 newtons. This obviously satisfies the first condition of equilibrium. We have our net forces is equal to zero. The second condition, torque equals zero, is also satisfied, as we can see by choosing the center of gravity to be the pivot point. The weight exerts no torque about the pivot point located at the center of gravity, since it is applied at the point and its lever arm is 0. So we're putting our center of gravity here, where the center of gravity of the person is, in between both forces. Then we know that our torque is 0 because our radius is 0. The equal forces exerted by the hands are equidistant from the chosen pivot point, and so they exert equal and opposite torques. The pole vaulter, holding a pole with its center of gravity halfway between his hands, has each hand exert a force equal to and half of the weight of the pole. So we can say that the force on the right equals your force on the left, which is the weight of the pole divided by 2, half. So here now we have the pole vaulter on the left side. And the forces that the hands exert are no longer equal. If the pole is held with its center of gravity to the left of the person, so in this figure, it's the right of the figure, then he must push down with his right hand and upward with his left. The forces he exerts are larger here because they're in the opposite directions and the center of gravity is along the distance from either hand. So choosing the center of gravity to be in the center of the pole causes our pole vaulter to have to put different forces in different directions from each hand. If the pole vaulter holds the pole as shown above, the situation is not as simple. The total force he exerts is equal to the weight of the pole, but it is not evenly divided between his hands. So if force on the left equals force on the right, then the torques about the center of gravity will not be equal since the lever arms are different. He is exerting different forces here because because there are different distances as well. Logically, the right hand should support more weight since it is closer to the center of gravity. In fact, if the right hand is moved directly under the center of gravity, it will support all of the weight. In this situation is exactly analogous to two people carrying a load. The one closer to the center of gravity carries more of its weight. Finding the forces FL and FR is straightforward, as in the next example shows. So for the situation above, calculate mass of the pole, which is 5 kilograms. We're going to calculate our force on the right hand, the force exerted by the right hand, and B, the force exerted by the left hand. The hands are at 0.9 meters apart, and the center of gravity of the pole is 0.6 from the left hand. Okay. So our strategy, there is not enough information to use the first condition for equilibrium. So that means F equals 0. We can't start off with that one. Since 2 of the 3 forces are unknown, and the hand forces cannot be assumed to be equal in this case because they're at different distances. There is enough information to use a second condition of equilibrium, which is net torque is equal to 0 if the pivot point is chosen to be at either hand, thereby making the torque from that hand to be 0. We choose to locate the pivot at the left hand in this part of the problem to eliminate the torque from the left hand. So we're going to say our torque on the left hand is 0. So here we are stating torque is equal to 0. So the torque counterclockwise and the torque counterclockwise or clockwise, they equal each other, and one of them is negative. So since our torque or our pivot point is on the left hand, let me show you in the image here. We're putting our pivot point on the left hand, so we only have our torque on the right and the torque on the actual pole. So we're going to equal our torque on the right hand equals our torque of the weight of the pole. So we know that torque is RF sine theta, but we know that theta here is also 90 degrees, so the sine theta goes away. So we have 0.9 meters, which is the total distance from the two hands, the left hand and the right hand. They are 0.9 apart. So that means if the center of gravity here, the pivot point, is on the left hand, it's at 0.9 meters apart from the right hand. And we're trying to find our force on the right hand. That equals the torque on the weight. So we have 0.6, which is the center of gravity here, and mg. So we rearrange here, divide by 0.9, and we end up getting 32.7 newtons. That's our force on the right hand. So for B, which is the force exerted on the left hand, the first condition of equilibrium is based on the free body diagram in the figure. This implies that Newton's second law, Fl plus Fr minus mg is equal to 0. Well, from here, we can say that Fl plus Fr is equal to weight because we made the pivot point on the left hand. So we can say that all the weight's going to be pointed on there. So this also equals mg. So we can just move the force on the right side to the left, or the force on the right hand that's on the left side to the right side. And we know our m of the pole, which is 5. We obviously know gravity. And we know our force on the right hand because we just solved that. So it ends up being 16.3 newtons that the left hand is exerting. So, like we mentioned before, if the closer you are to that center of gravity of the pole, the more force you're going to be exerting. So it makes sense that our right hand is exerting 32 newtons versus what our left hand is exerting, which was 16.3 newtons. So our answers make sense here. So that brings us to simple machines. Simple machines are devices that can be used to multiply or augment a force that we apply, often at the expense of a distance through which we can apply a force. The word for machine comes from the Greek word meaning to help make things easier. Levers, gears, pulleys, wedges, and screws are some examples of machines. Energy is still conserved for these devices between a machine, or because a machine cannot do more work than the energy put into it. However, machines can reduce the input force that is needed to perform the job. The ratio of output to input forces, force magnitudes for any simple machine is called the mechanical advantage. So MA for mechanical advantage equals your force output over your force input. So here, one of the simplest machines is the lever, which is a rigid bar pivoted at a fixed place called the fulcrum. Torques are involved in levers since there is a rotation about the pivot point. So here would be the pivot point. So you see that we're putting all of our forces onto the actual nail here. The only input force is here on the left side of the figure. Distances from the physical pivot point of the lever are crucial, and we can obtain a useful expression for the MA in terms of these distances. So here's our free body diagram. The longer the distance here, the easier the input force would be. And you'll see why here. For crowbars, seesaws, and other such levers are analogous to this one force, or to this one. Our force input is the input force, and force output is the output force. There are 3 vertical forces acting on the nail puller, the system of interest, from the previous slide. These are your input force, output force, and our normal force. Fn is the reaction force back, or the reaction force back on the system, equal and opposite to our output force. Note that the output force is not the force on the system. Normal force, or N, is the normal force upon the lever, and its torque is 0 because it is the exerted at the pivot point. The torques due to our input force and our Fn must be equal to each other if the nail is not moving to satisfy the second condition of equilibrium, which is torque equals 0. In order for the nail to actually move, the torque due to our input force must be ever so slightly greater than the torque due to Fn. Hence, our length I which times our Fi equals our length out times our F out, where Li and Lo are the distances from where the input and output forces are applied to the pivot, as shown in the figure. So we have Li here, L out here. Regarding the last equation, if we are to put all of our variables together, we have Li over Lo equals Fo over Fi. What interests us most here is the magnitude of the force exerted by the nail puller, which is F out, is much greater than the magnitude of the input force applied to the puller at the other end, Fi. For the nail puller, we have our MA equals FO over FI, which also equals, like we just said, Li over Lo. This equation is true for levers in general. For the nail puller, the MA is certainly greater than 1. The longer the handle on the nail puller, the greater the force can be exerted with it. So in the case of the wheelbarrow, the output force or load is between the pivot and the input force. The pivot is the wheel's axle, so that would be right here. Hence, the output force is greater than the input force. Thus, a wheelbarrow enables you to lift much heavier loads than you could if with your body alone. If the load has a perpendicular lever, which is example 9.3, of 7.50 centimeters, while the hands have a perpendicular lever of 1.02 meters, what upward force must you exert to support the wheelbarrow and its load if the combined mass is 45 kilograms? And B, what force does the wheelbarrow exert on the ground? So we have our length in and length out. So we're trying to find for A, what upward force must you exert to support the wheelbarrow and its load if the combined masses is 45 kilograms? So we have F out over Fn equals Li over L out. We manipulate that to equal to our F input, because that's the force that we're going to exert, our input force. So we know that our output force here is mg, 45 kilograms being the mass that's given for everything combined, and g, 9.8. And we know both of our lengths. So our input force would be 32.4 newtons. And B, what force does the wheelbarrow exert on the ground? So here we would have the free body diagram, which is this one up here, gives us the following force, which is F input plus our normal force would be our weight. Therefore, we have our normal force equals our weight minus this input force, which would give us 409 newtons. The normal force acting on the wheel by Newton's third law, the force is the force that the wheel exerts on the ground. So by knowing our input force, if you look at the figure right here, we know that this would be the force that the wheelbarrow is actually doing on the ground. So that solves for B. What force does the wheelbarrow exert on the ground? That's our normal force. Okay, here are more examples. A is a crank, is a type of lever that can be rotated 360 degrees about its pivot point. Cranks are usually designed to have a large MA. For B, a simplified automobile axle drives a wheel which has a much larger diameter than the axle. The MA is less than 1 here. And C, an ordinary pulley is used to lift a heavy load. The pulley changes the direction of the force, which is tension here, exerted by the cord without changing its magnitude. Hence, the machine has a MA of 1 here. More examples here. We have for A, a combination of pulleys is used to multiply force. The force is an integral multiple of tension if the pulleys are frictionless. This pulley system has 2 cables attached to its load, thus applying a force of approximately 2T. This machine has a MA of approximately 2. For B, we're adding another pulley. 3 pulleys are used to lift the load in such a way that the mechanical advantage is about 3. Effectively, there are 3 cables attached to the load. And for C, we're adding another pulley. This pulley system applies a force of 4T, so the MA is about 4. Effectively, 4 cables are pulling on the system of interest. System of interest being right here. So here we have A. The figure shows the forearm of a person holding a book. The biceps exert a force FB to support the weight of the forearm and the book. The triceps here are assumed to be relaxed. And for B, here you can view an approximately equivalent mechanical system with the pivot at the elbow joint as seen in example 9.4. So for 9.4, calculate the force the bicep muscle must exert to hold the forearm and its load as shown, and compare this to the force with the weight of the forearm plus its load. You may take the data in the figure to be accurate to 3 significant figures for this one. All right. So our strategy for this one, there are 4 forces acting on the forearm and its load, which is the system of interest. The magnitude of the force of the biceps is FB, that of the elbow joint is FE, that of the weights of the forearm is WA, and its load is WB. 2 of these are unknown, which is our force of the biceps and force on the elbow, so that the first condition of equilibrium cannot by itself yield FB. But we can use the second condition and choose the pivot point to be the elbow. Then the torque on the elbow, then the torque due to the force of the elbow is 0, and the only unknown becomes FB. So we're gonna just use what we know here. The torques created by the weights are clockwise, relative to the point, while the torque created by the biceps is counterclockwise. Thus, the second condition of equilibrium, which is our torque equals 0, becomes our radius 2 times our first mass, our first weight, which is the weight of the forearm, plus our radius 3 times our weight of the load, is equals our radius 1, which is the radius of the bicep, and our force B. Well, we're looking for our force B, so we're going to divide by the R1. And we know that our theta is equal to 90, so sine theta is equal to 1. We plug all this in, respectively. So we get our force on the biceps, or the force that the biceps are going to exert, is 460 newtons. Now, we combine the weight of the arm and its load, so that would be 6.5 kilograms times our gravity. That would give us 63.7 newtons. So that the ratio of the force exerted by the biceps to the total weight is as follows. So we have force B over weights A and B. We know that force B was 470 divided by our weights here. So that gives us 7.38. So this means that the bicep muscle is exerting a force of 7.38 times the weight that is actually supported. So here for A, good posture places the upper body's center of gravity over the pivots and the hips, eliminating the need for muscle action to balance the body. For B, poor posture requires exertion by the back muscles to counteract the clockwise torque produced around the pivot by the upper body's weight. The back muscles have a small effective perpendicular lever arm, RB, perpendicular, and must therefore exert a large force, FB. Note that the legs lean backwards to keep the center of gravity of the entire body above the base support in the feet. Here's 3 more examples. For A, a father carrying his son piggyback leans forward to position their overall center of gravity above the base of support at his feet. For B, a student carrying a shoulder bag leans to the side to keep its overall center of gravity above or over his feet. And C, another student carrying a load of books in her arms leans backward for the same reason. So they're all trying to find their center of gravity since they're adding the extra mass. So finally, that brings us to example 9.5. Consider the person lifting a heavy box with his back. For A, calculate the magnitude of the force FB uh, in the back muscles that is needed to support the upper body plus the box, and compare this to his weight. The mass of the upper body is 55 kilograms and the mass of the box is 30 kilograms. For B, calculate the magnitude and direction of the force FB exerted by the vertebrae on the spine at the indicated pivot point. Pivot point being right here at the end of his spine. Okay, so our strategy. By now, we sense that the second condition of equilibrium is at a good place to start, and inspection of the known values confirms that it can be used to solve FB if the pivot is chosen to be at the hips. The torques created by WUB and the W of the box are clockwise, while created by FB, which is counterclockwise. So what we'll do, we'll just equal all of our torques to each other here. We have 0.35 meters times our 55 kilograms. That would be, figure here. There it is. 55 kilograms being the upper body here. And we also know that it's at 0.35 meters, 35 centimeters, times 9.8 plus 0.5 being the distance of the box from the system, from the pivot, times its mass times its gravity, equals our 0.08 meters times our FB, force on the back, given right here. So we find B here being to be 4.20 times 10 to the third newtons. The ratio between the force of the back muscles over the total weight being 4,200 newtons over 833. This just being the addition of the two weights. So he's actually exerting 5.04 times the weight that he should be producing. So for B, more important in terms of its damage potential is the force of the vertebrae FB. The first condition for equilibrium, which is our net external force equals 0, can be used to find its magnitude and direction. Using y for vertical and x for horizontal, the condition for net external forces along those two axes equals 0. So we can use that. So for y components, this yields FBY minus our WUB minus our W of the box minus our FB sine of 29 degrees, because he is bent over at a 29-degree angle here, equals 0. So if we're just solving for FBY, you move everything else to the right side. So that gives us 2.87 times 10 to the third newtons. Similarly for the x components, we have FBX minus our force on the back muscles cosine of 29 degrees equals 0. So we do FB cosine of 29 on the right side, and that gives us 3.67 times 10 to the third. Now that we have x and y components, we just do the Pythagorean theorem. You square both and square root the result, and that equals 4.66 times 10 to the third newtons. And we can also find its direction, obviously, so that gives us 38 degrees when we do the FBY over FBX, inverse tangent of both. So note that the ratio of the FB to the weight supported is 5.59. So this force is about 5.6 times greater than it would be if the person were standing still, upwards, erect. The trouble with the back is not so much on the forces that are large, because similar forces are created in our hips, knees, and ankles, but that our spines are relatively weak. Proper lifting performed with the back erect and using the legs to raise the body and load creates much smaller forces on the back. In this case, 5.6 times smaller. So if this person were to be standing straight up, this box wouldn't feel so heavy on it. And that concludes chapter